the absolute pleasure to introduce Dr. Reid Ferber for this month's seminar series. Dr. Ferber is a professor at the University of Calgary with joint appointments across faculties of kinesiology and nursing and the Cummings School of Medicine. Reid is an innovator, a disruptor, and an internationally recognized leader in biomechanics research and wearable technology. I think many academics have great ideas, but few can put them directly into practice, and this is where Reid thrives. He's the founder and the director of the Running Injury Clinic and various technological solutions that put biomechanical innovations in the hands of end users. He's a man that wears many hats as well as many bow ties, as you can see today. And he leads a team of University of Calgary researchers in the NSERC Wearable Technology Research Collaboration, the WeTrack CREATE program, to train the next generation of wearable technology experts. He's also my PhD supervisor and remains an important mentor to me and a role model for myself. So I'm very honored and excited to welcome Dr. Reid Ferber to our speaker series today. Thanks for joining us, Reid.
Thank you, Dylan. I think that was one of the nicest introductions I've ever received. I really appreciate that. It's a pleasure to be able to speak to your group today. I hope that you find this kind of fun, kind of informative. I hope I don't embarrass Dylan. I'm going to tell a couple stories, maybe just one story about Dylan. It's a good story, though. As Dylan knows, I am a bit of a storyteller, so I'll kind of weave that into all of this. So I apologize for I'm a big fan of technology, but sometimes technology fails us, but I'm glad. Thanks for being patient with us here. I am going to talk about the WeTrack program here, and maybe from a brag standpoint a little bit, but also just to kind of set the stage for what's going on from a research perspective. What is my lab concentrating on, and how does that kind of go across, I think, wearable technology research in general. And I hope to send you away with some pretty practical information that'll maybe improve or at least inform your research. So at the end of the day, I hope there's one good idea that comes out of this. So I have the pleasure of directing the Wearable Technology Research and Collaboration, or WeTrack, training program. As Dylan knows, I'm a big fan of acronyms, and WeTrack just kind of, it's sung to many of us when we were looking at what we should call this beast that is a CREATE grant. I started writing this, I started coming up with the idea in about 2016, where the Vice President of Research, who is now our President, Ed McCauley, had a call for new ideas on campus. And for each of our research themes, one of those being engineering solutions for health, he put up $1 million. And that money was to be split between 3 to 5 groups. And we did it in a bit of a Dragon's Den style pitch idea, if you will. But it had to be new collaborations from different faculties, and you had to have a clear strategy about what are you going to do with this collaboration. So again, I like acronyms. We came up with the STIM project, or Sensor Technology and Monitoring Movement. And it all came about because a professor over in geomatics approached me one day and they said, hey, we've got some really cool technology that's helping us to navigate using Wi-Fi, or not using a combination of Wi-Fi, but also just the accelerometers, gyroscopes that are in a smartphone, so that you can move around, or we can figure out where you are in the world independent from GPS. So think about if you walk into a mall, for example. And the technology was outstanding, and this particular professor said, we actually have no idea how somebody walks, so we don't even know what some of the data looks like for the most part. So he and I got together, we applied for this competition, if you will, and then that we were one of 4 groups that received funding, and then that led to, well, let's grow this up now and let's try to make this as campus-wide as possible. And we were very fortunate. We applied in 2017 and we received the grant in 2018. So we are just coming up on our, so we've been into it for a little over 4 years now. So the WeTrack training program, we are not focusing on hardware at all. I say over and over that we are hardware agnostic. I don't care what kind of wearable devices are out there. I don't really want to be developing them because that takes a lot of resources. We want to be on the practical application side, the software side of things. So it could be wearable sensors to track step count, heart rate variability, sleep patterns. It just doesn't matter. We take that data, we generally apply machine learning methods, because with wearable technology, you actually have an overwhelming abundance of data. So we try to apply machine learning methods to those, and Dylan is one of the pioneers within my group of introducing me to the idea of how machine learning can be utilized in terms of wearable technology data. And we do this to improve performance. It is an NSERC grant after all, so you're not allowed to talk about injury or health, but we also focus on predicting injury as well as optimizing healthcare within the WeTrack grant. Part of what we have accomplished here is this is Canada's first specialization in wearable technology, so it's a formal specialization on campus. Currently, we have the specialization approved across 7 different faculties. And when students graduate, for example, here in kinesiology, they would graduate with a PhD in kinesiology, and then on their parchment it would say with a specialization in wearable technology. Now we bring in 2 kinds of students. We either bring in students who have already had training in terms of human movement, so biomechanists, kinesiologists, exercise physiologists, mechanical engineers generally come with training in terms of human movement to a certain degree. And then we cross-train those students with respect to data science. Or we bring in data scientists who have never worked with humans before, really, and we cross-train them, and they receive coursework and training in terms of human movement. And then everyone receives entrepreneurial training through the Haskayne School of Business here on campus. Specifically, we have courses for non-business majors in entrepreneurship and design thinking. And then everybody has the opportunity to do internships with companies that we've partnered with. And when I first wrote the grant, I actually spent a lot of time cold calling wearable technology companies across Canada. And I think I had 17 on board when we first submitted the application. And that was in September 2017. And by the time we found out about that we were successful with the grant, about half of those companies had gone bankrupt. And that is the world of wearable technology right now. We currently work with 35 different companies. About half of those are in Calgary, and 80% of those are startups. There's a lot of wearable technology startups that ebb and flow. They come up with great ideas and then run into cash flow problems or regulatory issues, and they just kind of have to fold and or sell their technology over to other companies. So it's a nice program that we built. It's a nice specialization where students do these internships. They get this entrepreneurial training. They get cross-trained in either human movement or data science. So currently, we are supporting, we have 56 students. We were actually slated, we budgeted to have about 34 supported at this point in the grant. But about 80% of our PhD students are successful in getting their own funding. So we're leveraging and we're bringing in $1.28 for every dollar that NSERC gives us. So in other words, we recruit a student and we're paying them WeTrack money when they first arrive, and then they're successful getting their own NSERC PGS grant or CIHR doctoral grant. So we're thrilled that we're able to bring in these high quality students. We have a nice balance between male and female students as well. As I said, we have a little over 35 different local, national, international companies, many of whom are here in Calgary. For some reason, Calgary seems to be a bit of a hotbed for wearable tech startup. And I think that's for 2 reasons. One, Calgary Economic Development and the City of Calgary have made life sciences and technology startups a priority in terms of providing them with opportunities to come here and bring their companies. And as well, we have Garmin Canada, who just actually announced, today's Friday, I think they announced this on Tuesday, they're doubling the number of people at the Cochrane location just west of Calgary. So they're nearly doubling in size, and Garmin serves as an anchor tenant, if you will. And I think that's attracting a lot of these companies to come here because Garmin is here, and a number of other successful companies that I've listed as well. And then finally, we're collaborating across 36 different research labs. So when we first started, there was the core 10 applicants, and we've grown that. We've over tripled that. So these 56 students are spread across 36 different labs, across 7 faculties here on campus. So it's a big program. I don't know if I would call it successful, but we're doing some super fun stuff. And if nothing else, I have fun. And I think that's the marker of success that I like to go by. So again, we're using machine learning, using big data. It's evidence informed. We talk with these companies. What are their pain points? What do they need help on? We talk to other clinicians about how could wearable technology be integrated best in terms of their clinical practice. And we're trying to match these clinical needs with research questions. And that's really been what I've tried to focus on in my career here at the University of Calgary. The other part of this that I just want to highlight is when we first got the grant, I started to receive a number of emails and phone calls from professors on and off campus. But for those on campus, they would say, hey, we just got a CIHR grant. We're looking at, I don't know, sleep patterns in adolescents. Oh my gosh, this is an overwhelming amount of data. What do we do with all the data? Or I would receive a request from somebody saying, oh, we're putting in a grant. What should we be ordering, and what's our research management plan in all of this? And at the same time, I actually got a cold call from the city of Calgary. One of the directors of transportation called me and said, can you help us understand where people are cycling in the city? And I said, sure. And just as an aside, I said, well, how do you do it now? And they would actually hire about 20 people to sit in lawn chairs on street corners with a clicker. And they would do that 4 mornings in June, July, August, and September. And that's how the city was trying to track cyclists. Just by, if somebody cycles by, they click a button and add it up. And I said, yeah, wearable technology kind of affords us the opportunity to see a lot more, in a lot more detail, how many people are cycling and where they are. So the city gave me some money. I went and got some grant money. The university gave me a little bit of money. And we created this wearable technology citizen science program. So this is a level 4 secure server on campus. Level 4 is necessary because there's a lot of sensitive and private data that comes with wearable technology, using a piece of wearable technology. And this was also a way for me to get more data. I really like data. And I'll tell a little story about that here in just a moment. So this is how we support research on campus when somebody has a wearable technology based research project and they're using a Fitbit or a Garmin or something along those lines. This level 4 secure server serves to help them store and manage their data securely and privately so that they don't have to worry about either hiring a software engineer or even dealing with that much data. This also serves as a way for just everyday citizen scientists, such as yourselves. I guess I'll do a little pitch here. You too can become a citizen scientist. We have a few thousand people that have just donated their data. So they've signed up to become citizen scientists. And when they do that, they allow us to go into these company servers, grab their data, and pull it into our server, and then we update it. So if a researcher wants to do a project, then the individual signs up as a citizen scientist. We link them to a research study, and then every week we update their data. So the researchers don't have to worry about that, and we actually send out reports in terms of adherence and how much data is there and what their people were up to on a weekly basis. So the level 4 secure server was a way to allow our researchers to take that burden off of them, but also give them an opportunity to access data they would not have the ability to access otherwise. The nice collaboration for me, as one example, is I actually work with researchers in urban design, because they now have access to the cycling data that I was just mentioning. They understand where people are cycling. We can actually go back 2 years, so they could see how cycling activity occurred 2 years ago before infrastructure was changed by the city. Just changing the timing of lights or installing bike lanes, for example. So it's opened up some really nice collaborations for us. All right, I know I've told a couple stories, but now it's story time. So I actually got into wearable technology probably back in 2008. I had a patient, and I asked her a very simple question. She was injured. She probably shouldn't have been running, but runners are a little bit insane. And I asked her, what are your plans for the week? What runs are you going to go on? And she said, well, I was going to go for a run today, but I left my Nike chip at home. And I didn't understand what she was saying to me. I said, sorry, what? What's a Nike chip? And she said, oh, it's this little thing that tracks my mileage. And I don't want to go for a run because I don't want to miss out on having my mileage tracked. I'm in a competition with my friends. So I really needed to explain this. So she explained that it was this little device, as you're seeing in front of you. There was a space in a Nike Air Pegasus shoe. If you lifted up the insole, there was a little space where the Nike chip went, and then that information went to an iPod. Many of you are too young to know what an iPod is, but it predates the iPhone, and it was a music playing device, MP3 player. And this is a way to track your mileage. And it stunned me that this individual's behavior was being changed because of this device. And that's really the goal of researchers. We're trying to change people's behavior. And here this device was doing it. So after this patient left, I actually turned to my research manager, who Dylan knows well, and I said, I want to start collecting accelerometer data from everybody. And he said, okay, what's our research question? I said, I have no idea. We just got to start doing it. And I said, let's put it on the center of mass, just so we get a general idea of how they move. So every patient, every research subject who came in through the clinic, we started collecting accelerometer data from. And I didn't know what we were going to do with that data. Dylan actually wrote one of the first papers where we brought in the entire University of Calgary Marathon Training Group, about half of which were experienced runners. They were coaches. They'd run multiple marathons. And the other half, they had never run at all. They were running not only their first marathon, but most of them, they were running for the very first time. And they engaged in this 10-month training program. So we collected all of their data, and we were bringing in varsity athletes as well. And so Dylan actually pointed out, you know what, we have a lot of soccer data from soccer players, and we have all these experienced runners, and we have all these inexperienced runners. And we had been formulating ideas as a research group about understanding, like, what family do people belong to? You know, if like males and females run differently. That was a paper that we published, I think, in 2003. It's not rocket science by any means, but it's just understanding injury patterns. Female runners have different injury patterns than male runners. And I really wanted to understand that, so we started looking at that. And we also know that more experienced runners have different injury patterns than novice runners. So Dylan actually published one of our first papers looking at how do we use machine learning to look at the vast amounts of data that come from these devices, and can we properly categorize people? And you can do it quite accurately. So that was just that's kind of how the genesis of all of this started. It started with one patient telling me that she forgot her very inaccurate. By the way, the Nike chip was terribly inaccurate, like horribly inaccurate, but their website was magnificent. The engagement that people were getting from it was unbelievable to me. And it just kind of set the stage for wearable technology as a launch pad from that point on. Well, let's fast forward a bunch of years. I actually received, well, I've been fortunate, I received a number of grants. And one of those grants was from NSERC. And this is called an eye-to-eye grant, an idea to innovation grant. And we were looking at injury prediction methods. And so not only do men and women run differently, and experienced and inexperienced people run differently, but this was our first attempt at collecting these types of data outside the laboratory setting. So we had people do a very simple exercise or very simple conditions. They ran 2 kilometers on the sidewalk, and then they took a step to the left, and they ran 2 kilometers on the grass. And we just wanted to see, like, how different are these movement patterns on different surfaces. And we're not doing this because we're, a runner knows if they're running on the grass or not, but we just wanted to understand what are the subtle differences in their overall running mechanics. And when we started to look at some of the data, well, you can see this nice repetitive pattern going on, and all of a sudden there's this huge spike in their medial lateral acceleration. So we've got a three-dimensional accelerometer. It's attached to their low back to approximate their center of mass. So the signal should be dominated by a vertical acceleration and maybe a little bit of anterior posterior acceleration, but they're running a straight line. They're running down the sidewalk. There should be no medial lateral acceleration, but we're seeing these huge spikes and we didn't understand it. And I had a fantastic postdoc at the time, Lauren Benson, and I'll never forget Lauren. We're all kind of looking at the data, and Lauren said, well, we can just filter that out. We can just get rid of that. But then we noticed it in another research subject. I had a few of these spikes. So then we started looking at the equipment. Maybe the equipment's faulty. Maybe we're getting artifact data from this. Maybe we're not securing it properly. Maybe they're shifting their clothes around or shifting the belt. But that wasn't the case. Then we started to figure out that this is actually only happening when we collect at noon. So if we're collecting at 9 o'clock in the morning or 10 o'clock in the morning, we're not seeing these huge spikes. We're only seeing it when we start collecting at noon. And then we just started paying attention to what was happening. And if somebody's running down the sidewalk at noon, chances are somebody's walking towards them or somebody's walking their dog. So what they're doing is they're jumping off the sidewalk to avoid these other pedestrians, and they're jumping back on. And that's what's causing these big medial lateral accelerations. So I just kind of put a stop to everything, and I just said, like, whoa, whoa, whoa. We're collecting data out in the real world, so we need to account for the real world. In a laboratory setting, you don't worry about external factors. In your lab, your weather is the same. The temperature's the same. If they're running down on an open area and you're collecting running biomechanics during overground running, nobody's in their way. They're not jumping over or moving away from obstacles, and certainly on a treadmill, they're just running on a treadmill. So now that we're out in the real world, we have to start figuring out, like, what does this look like? And fundamentally, do people run the same day to day because these external conditions are always going to be changing? So we actually shifted our thinking altogether, and instead of this running on grass, running on sidewalk, we just started to answer the question, well, how many runs do we need to collect once we're out in the real world to really build or understand what is typical behavior for this individual? And again, because people don't run the same route all the time either. So there's going to be subtle differences in all of this. So when you move outside the laboratory, all of a sudden you have to consider weather. And you even have to consider uneven surfaces. We learned a lesson in that 2 kilometers. The first kilometer was on sidewalk, and you're running right beside the Olympic Oval, away from the Olympic Oval. And then you turn a little bit, and you're running now down an area which is a tree-lined street. And those trees have roots, and those roots actually knock up the sidewalk. So now you actually can't collect sidewalk data because it's 2 different sets of data. It's smooth sidewalk versus uneven sidewalk versus grass. So it wasn't our original research question at all, because the trees now play a role in terms of what does the run path look like. Certainly now they're running up and down. There's slight elevation changes that you have to account for, whether they're running uphill or downhill. And again, you have to watch out for other runners and pedestrians and dogs. People are out with their dogs as well. So we just started going down this path of, well, how many days of data do we need to collect? So this is a 6-dimensional problem, but I'll show it here in a 2-dimensional plane. So this is vertical oscillation. This is how much they bounce up and down, and this is one person going for a run. This is a 2-kilometer outdoor. Every dot is a step, and this is how much they bounce up and down, and this is how much their pelvic drops, how much their pelvis changes in terms of frontal plane motion. And then if we just take this circle, we've just drawn this large enough so that we encapsulate 95% of their data. So on average, this is how this person runs on this given day in terms of how much they bounce up and down and how much their pelvic drops. Well, fast forward 2 days later, and they went on the exact same run, and none of their strides were the same. I don't know why that is, but what we do know is that people do not run the same. They don't walk the same one day to the next. So this is the exact same run, but they are running very differently. And I think there's a lot of internal factors that go into this. It could just be how they felt that day, how much sleep they got. Maybe we scheduled them for a slightly different time of the day. Could be the clothes that they're wearing. We didn't control any of that. We just asked them to show up. We kind of abandoned all possibility of controlling all these factors that you would in a laboratory setting. So to make a long story short, if you look at multiple runs, so this is now their 5th run. If you can see, like this little red point over here is the same as this little black point over here, and then these dots are encapsulated into these dots. So this is a 5th run. There's 4 black runs in here that are needed so that we can encapsulate 95% of their data to understand, okay, what is a typical pattern for this individual? And then can we take a 5th run or a 6th or a 7th? And how do we, so we randomized all of this to be able to say to you with confidence, you need 4 to 5 days worth of data to define, in this case, a stable gait pattern. So you have to have at least 4 to 5 days, depending on the variable that you're looking at, in order to have confidence that if you were to collect data down the road at another given time for a similar route or similar-ish type route, that you would be able to collect reliable data that is indicative of how that person moves. So when we published this paper, we published it, and then at the same time, another paper came out from a different lab altogether that basically had the same result. They were looking at ActivePal devices in terms of just measuring overall behavior. How much time are they seated? How much time are they walking around? Minutes of vigorous activity, sleep patterns, etc. They actually went one step further. This Aguilar-Farias paper, they went one step further to say, if you want to look at activity patterns for an individual, you have to include at least one weekend day. You need 4 to 5 days worth of data, and one of those days has to be a weekend. You know, I can't see everyone here, but I usually, when I do a poll with the audience, I'll say, how many of you are more active on the weekends? Usually about a third of the audience holds up their hands. And I say, about how many of you do nothing on the weekends? You just rest. And about a third of people do that. And then about a third of people, you know, will maintain about the same relative activity pattern. But you can imagine if you're fairly active, if you're working out on the weekends or moving around, and you just want to take the weekend off, well, that has to become part of your profile in all of this. So we were thrilled that around the same time, this other lab had the same result for different variables of interest using a different piece of wearable technology. So we went on to then look at this in terms of, does it matter about inclination? Because people run very differently when they go uphill, very differently when they go downhill as compared to level ground. So this first study only involved maybe a dozen people, and we collected 12 runs. Then we would randomly select runs and start to figure out how many runs to build this profile. This second study by Nizam, which is another postdoc of mine, you know, Lauren was still involved in this study. Dylan had obviously left by then. Nizam had a group of 35 individuals, and we used 8 days worth of running, both uphill and downhill. And this was our first use of kind of the citizen science approach, where we had data from people that we didn't control anything about it. And I can also say, so it takes about 4 to 5 days worth of data. We confirmed that again, and it actually doesn't matter how hilly the run is. So people are going to have very similar patterns uphill, downhill, on level ground. And then this was a funny paper that actually took a while to get published, but we also wanted to look at, well, how much does weather play a role in all of this? I actually got the idea because my lovely wife had enrolled in a half marathon training program, and she had 2 long runs that were back-to-back on back-to-back weekends. And the second run, she came home and it was just gale force winds and sleet, and it was just nasty weather. And she remarked to me, she's like, "Oh my God, that run was so much harder than last week. It was the exact same run." And all of a sudden I just got super excited because we had 2 sets of data for a large group of people. There's about 30 people involved in this training program who ran in relatively good weather conditions one week and then did the exact same run with terrible weather conditions the next week. And yeah, people run differently when the external weather conditions change. You know, this is not rocket science. We probably could have figured that out, but you can't run these studies in a laboratory setting. You can maybe turn the temperature down a little bit, but you can't mimic wind blowing and snow on the ground, ice on the ground as well. So all of this went into trying to help us understand, you know, how do we use this wearable technology data? What are the parameters from a methodological standpoint if people are going to move outside the laboratory? So you have to consider temperature, whether it's hot out or cold out, because you know people are going to put on more cold clothes. That's going to restrict their training. People often change their footwear, which plays a minor role in all of it as well. You have to consider uphill, downhill, as we mentioned. A new route. You actually have to consider whether this is a new route for someone, because people will slow down if they're running a new route, as opposed to if it's the same route that they're used to, they will run a little bit faster. Same with running with a group. If people run within a group of individuals, everyone adapts their speed usually to the slowest runner, and people run in cadence. Same with music. People will naturally assume a cadence to the beat of the music that they're listening to. So velocity plays a role, and then what they're running on also plays a role. People run differently on pavement than they do on gravel than they do on a run path. A run path has a very different camber to it as compared to a sidewalk or certainly pavement. You know, there's a camber to that in order to get the rain to flow off of it into the gutters. Not so much on the run path. It's fairly flat, and it might be they don't really consider the angle of the run path necessarily when they're laying down that type of material. So all of these extrinsic factors need to be considered. That's why you actually have to collect way more data than just the typical, you know, 1 day's worth and a few conditions or a few strides from an individual. Now, we've also, as of late, been trying to figure out, well, what data can we collect indoors that will translate to outdoors? This all came about because we published a systematic review in 2018, and it was based on information that we could gather up to 2014. So I'm sure as many of you know, it takes a long time to get a systematic review, collect all the information, go through the process of screening it, and then writing up the paper and getting it published. So this finally got published in 2018. It was based on 2014 data. And here's the number of running and walking studies that had been published outside the laboratory setting using wearable technology. And the main condition we had was that the data had to involve more than 200 meters. Just that's it. 200 meters of data, of walking or running data, had to be collected, because people were still using it for only collecting a few strides of data, even though it was outdoors, for example. Sometimes it's just a methodological problem. They're still using wired accelerometers, or sometimes they're just kind of stuck in these methodological ruts, if you will, of, well, I've always looked at 3 to 5 strides in my lab, I'm going to look at 3 to 5 strides here out in the real world. So we then published a follow-up systematic review. It was just published last year, and as you can see, there's been this massive exponential rise in the number of studies looking at walking and running outside the laboratory setting. So I don't know, I thought we came up with a fun little title for this one. You know, for this systematic review, is this the real life or just a laboratory? Because one of our main findings from this systematic review is that 72% of these wearable technology studies were still being collected indoors. in a laboratory setting or an indoor track. And most of these studies were talking about how this could help and be translated to outdoor real life activity, but we just don't know what data translates indoors versus outdoors. And still, over 2/3 involved limited strides and distances under 200 meters, because we wanted to include as wide of a breadth of studies as possible. So that kind of led us to this most recent study where we've got a whole bunch of runners, and this is just outside the Olympic Oval in the Faculty of Kinesiology. Lovingly, we call this the Big Red Paperclip. It stands for Citius Altius Fortius, and it was erected for the Olympics. You can actually see the Olympic flame. It's not lit, but you can see the cauldron just back there. But this is where we would meet people, and this is the start of their 2-kilometer run. So they would, and we didn't even choose it. We just said, well, run to the left or run to the right, and you're going to go this far if you go to the left, and you're going to go this far if you go to the right, and turn around and come back. So we're letting them do a 2-kilometer run outdoors. We're not controlling anything with respect to, the only thing we tried to control was we tried to collect the data in late summer, early fall before the snow fell. And then we would randomly either meet them here at the Big Red Paperclip, or we'd meet them at the Jack Simpson, which is just around the corner, and we'd have them do a 2-kilometer run on the track. And the goal is to try to figure out for each individual or for this group, what measures that come from the accelerometer. We had one on the foot, on the tibia, and the low back. So what measures are ubiquitous, whether you're indoors on a track, in a laboratory setting, or outdoors in the real world? And I'll kind of cut to the chase here, but so here's one subject, and this is adjusted braking speed. So every time their foot strikes the ground, there's a braking force that comes back. So for this individual, if they're indoors, that's red. They have a much lower braking force. Oh, don't know why that happened. They have a much lower braking force as compared to outdoors. They have a higher braking force, and it's very different. Whereas this subject 11, they pretty much have the same in terms of braking force. And we've analyzed a number of variables, but I just kind of want to keep this big picture and cut to the chase here. These two people are they're two different people. We can't combine these data together. I've never been a fan of group-based design, probably for the last 15 years. Everything is about how does one individual react to either this intervention or how do we treat them clinically. So the takeaway from this indoor versus outdoor study is that there are large, I'll say huge, inter-subject, inter-trial differences, and it makes it very difficult to generalize indoor data outdoors. So if you're wondering, how does my data translate outdoors, you should probably collect your data outdoors. So wearable technology is a wonderful thing because it enables us to move outside the laboratory into these more real world settings. As researchers, though, based on that systematic review, 72% of the time we're still collecting the data with wearable technology indoors in a laboratory setting, and we're hoping that it translates, but it just doesn't. People move very differently indoors versus outdoors. There's too many external factors that you just can't control as a researcher. Okay, I'm just going to go through a couple others. Like we spent so much time on just the methodology side of things. This was looking at different running environments, treadmill versus indoors versus outdoors. That was a nice little paper as well. We looked at changes during a marathon. Christian Claremont, who's good friends with Dylan, they actually both came from the University of Regina, and John Barden's program there. They produced wonderful students. Christian had the opportunity to collect data from about 20-some individuals who were running a marathon. They actually it was marathons from all over the world. But because of this citizen science program we have, the data were available to us. And he published in a really nice paper that fatigue patterns for experienced and inexperienced runners are very different. And they're different by individual as well. People just fatigue in a very different way. So you need to look at them from an individual standpoint. This was a nice paper that, again, Lauren Benson published, where we actually provide all of our automated algorithms. We provide the code for trying to figure out what are the best ways to partition the data, how do you calculate certain variables. So we publish this in Sensors, and there's a whack of data, as well as all of our algorithms are freely available. And then we actually did a specific study looking at, is classification accuracy improved using subject-specific or group-based designs? And the long story short, subject-specific designs provide us with a much higher classification accuracy as compared to looking at two groups of say injured or uninjured, or older, younger, for example. Because there are some, in that specific regard, younger runners, they run a little differently than older runners, but there will be some misclassification, if you will, where there are some older runners that actually have gait patterns more similar to younger runners, and vice versa. Younger runners, actually, there are some that run more similar to older runners. So you just can't lump people together in these groups. I think building these subject-specific models is critical, and collecting multiple days worth of data is absolutely necessary for you to understand whatever your intervention is, and or to just kind of move this type of research forward and out into the real world. So I'll kind of come to a bit of a close here. I think I'm probably a little over from what Dylan asked me to do. I'm always long-winded. Dylan knows that about me quite well. So I strongly feel, not just the biomechanics community, but just researchers in general, people who are utilizing wearable technology, we have to embrace new methods as we move the laboratory out of our laboratories. We know that we need 4 to 5 days worth of data, whether it be for activity patterns, just general activity patterns, gait patterns. Other studies have shown this as well. Driving patterns was one. There's a geomatics professor that we collaborate with who also showed that you need 4 or 5 days worth of data to understand driving patterns when tracking them using GPS technology. And then you have to now embrace, you have to love these extrinsic factors. You know, weather is no longer an enemy, it is your friend. You need to embrace it, and you need to understand, well, what was the weather like that day? How maybe did that influence my results? There's lots of extrinsic factors. You know, pedestrians, weather are probably two of the biggest ones that we have to compete with when we do our studies. So let's go back. I have been very fortunate in my career certainly this is an NSERC Create grant that we've talked about, but my very first grant as a young researcher about 20 years ago was from Alberta Innovates. We have a granting program here. And so I've received funding for both the health solutions side as well as technology future side, and that's to kind of move our technology forward. National Research Council of Canada has been fantastic, and certainly CIHR has funded a number of projects for us as well. So I thank them. I thank you for listening. I thank you for the kind invitation. I'm going to stop sharing, and I'm happy to answer any questions you might have. Yeah, no applause necessary. Thank you.
Thanks so much, Reid. That was great. Put it out to the audience here. If people have any initial questions to kick things off.
Hi, I have one question. I'm not an expert on gait pattern, but I'm curious about what do you mean the pattern? For example, in your early examples, you have a two-dimensional plot. Then on that two-dimensional plane, you fit a circle. So
Yeah.
is that like one example that the circle is kind of one gait pattern? Yeah, that's my question.
Yeah, so the way we did that is, so we received 6 data points in terms of pelvic drop, vertical oscillation, braking force, overall gait velocity, cadence, stride length, for example. So, and what we would do is we'd randomly take any 3 variables and fit a 3-dimensional sphere to it. And then, so we would know the size of it, and certainly we had to standardize the data itself. And then we repeated that until we understood, okay, what sphere best represented the dimensionality of their data itself. So I just showed it as a two-dimensional plane, but it was just it was almost a simplistic way for us to wrap our head around how do we determine the 95% confidence intervals for as much data as possible. So that's how we went about it.
Yeah, so usually it's a high dimensional feature, right? Space.
It is a high dimensional feature, absolutely, and we're fitting a three-dimensional sphere to it using random generation or random combinations of the 6 different variables.
Oh, okay. Yeah. All right. Yes. Thank you.
I have 2 questions. Ray, thank you so much for the talk. It's very interesting, and I can feel your passion in wearable technologies. My first question is because I'm a computer scientist, so I'm more interested on the data analytics side of things. Based on your experience, like where you see the gap, like for example, have you had difficulty like applying existing machine learning tools to analyze your data and to extract useful information? Like, do you feel there are things that we as computer scientists can further develop? That's the first question.
That is an excellent question. So I think one of the, okay, I'm gonna be very clear about this. I always say I'm not gifted enough to be a clinician. I'm not smart enough to be an engineer, and I know enough data science to make me dangerous. So I'm not an expert at any of those 3, but I'm the person who can talk to all 3 groups, I think. In speaking with, we've actually published a paper on this. Daniel Fuller is out of Memorial University. I think one of the biggest problems in advancing the field of data science is not having enough data sets publicly available so that people can use the same data and apply new and different techniques to really advance that side of it. So from my standpoint, I really can't answer, what data science techniques are best or most useful. We are working hard to open up the citizen science database so that anybody can play with the data, and a machine learning expert such as yourself can then advance your area of science because you have access to this enormous database that everyone else has access to as well. So that's a big thing that we're pushing for, is to get this information publicly available, especially for data scientists.
If you don't mind, I actually have a follow-up question on that. So in that project, how do you label the data? Like you can collect wearable device data, but you don't have information such as poses or activity, especially the precise onset and offset and activity. How the labeling is done.
Yeah, wearable technology data is unbelievably messy, without a doubt. So when somebody signs up to become a citizen scientist, we know some very basic information about them in terms of their overall demographic makeup. We also collect an SF-36 and a few other surveys about them as individuals and self-reporting type information. And then we do collect, so on a daily basis, we will collect just daily summaries of data. Everything that your watch gives you in terms of, here's how much you slept, here's how many steps you took today, here's your average heart rate, all of that information goes in there. And if somebody has an event defined as they wanted to go for a bike ride, well, as soon as they hit the start button, now we start getting very granular data about GPS location, heart rate, many other metrics that whatever metrics that device captures. Could be blood pressure, estimates, or SpO2, and then we get all of that until they hit the stop button, and that's defined as an event. So we have about 2,000 citizen scientists. They provide us with about 7,000 events a week. So in addition to their daily summary, so we have millions of data points from these wearable devices. But what we don't have is information about injury or health status. That's where it comes in. We are supporting about 13 different studies on campus who are providing all the same information, but for cancer patients doing rehabilitation or yoga therapy, for example, or hemodialysis patients. We're looking at activity patterns leading up to receiving hemodialysis and after hemodialysis. So there are researchers who are gathering lots of that granular type data about this health status of their patients, and then we're helping them by gathering all of the wearable technology data for them. And then we, of course, link all that up from a research perspective.
I see. Okay. So the label are either collected from the user device or maybe explicitly provided by the citizen scientists themselves.
Correct.
My second question is related to the CREATE program. I can see you're running a very successful CREATE program, and we are in the third year of our CREATE. So I want to ask, like, if you look back, are there things that you wish you know at the beginning of your program?
My gosh, I wish I knew how many more grants I had to write in order to support the CREATE program.
Okay.
Nobody told me that. I think that's my full-time job now, is just writing grants, especially for equipment. So we are fortunate to, we've received a couple CFIs. I've received an NSERC RTI to get us a lot of equipment, because if we're going to bring in all these students, we need equipment for them to use. I think the biggest lesson that I learned is collaboration is not automatic. And I probably should have had I think we've moved towards a nice collaborative model where we're at right now for most of WeTrack, but I can see that some people have kind of gravitated into their own worlds again, and we're not staying in as good a contact with them or engaging them in the bigger picture, and leveraging our funds. I've left that mostly up to the students. As I said, we're bringing in $1.28 for every NSERC dollar given to us in terms of student funding. We could have been a little bit more active on the operational side of things if our researchers had some more resources in the beginning as well. So I feel like we ramped up starting in about year 3, and now we've really exploded in terms of number of students and number of projects that are going on. But that was all because so much of mine, it took 2 years to set up the level 4 secure server, to get the funding in place, to hire the software engineers, to liaise with research computing services. That was a monumental effort. I had to do that because the original idea in the grant was that we were going to collect data from all varsity athletes, Olympic athletes, and intramural athletes on campus and have that data available. But COVID hit. Well, the first problem that we ran into is that all the coaches said, oh, that sounds like a great idea when we were writing the grant. And then it was hard to get access to those athletes when they're actually in season. So we're having difficulty there. And then COVID hit, and then now we can't collect data on anyone. But we had just pushed the citizen science program to the point where we opened it up, and now data started flowing to us. And we published, I think, some fun papers from collaborators around the world in terms of running patterns, before and after lockdown, behavioral activities in different regions of the world based on lockdown restrictions. So it kind of opened up a new world for us. I wish I had thought about how to make all this wearable data available sooner.
Yeah, thanks for sharing.
Yeah, I have some questions, but I want to open it up to see if there's any other questions from the floor before we go. I guess we have till 2 here. So maybe briefly then, Reid. I know one of the things that you mentioned, and something that we would always try to do, is the agnostic side of it, right? The sensor agnostic side of things, which can be really beneficial, but it can also be really challenging. I think that's something that I think we deal with a little bit in this grant, is that people have very, very different equipment that's being used. Some people are using very like commercial type sensors, like, you know, smartwatches and things. And then other groups are developing their own hardware because we span, you know, engineering and computer science. And I guess maybe just a broad question of what level of that, I think you're probably more on the commercial side, but how has that agnostic side helped or hindered things?
Yeah, that was a hard decision that I made. It came with a lot of pushback because we have engineers in our group as well who were anxious to build new stuff. And I quite simply said, we're not funding any grad students who are working on the hardware side of things, because I wanted there to be collaboration on specific topics, like around software or around analysis of data. So I think it helped us. It came with a lot of pushback to begin with, but now it's really helped us to advance what we're doing, because we have all these new people coming in asking us for assistance from a data science perspective, from a data management perspective. And we have all those tools built in at this point. Whereas I think if we had have divided our attention, and some people were using their own devices and collecting their own data, that data is never or rarely, or I'll just say extremely difficult to get into the citizen science database. So now that lab becomes functioning on their own in their data. They could share it, but we don't have an easy mechanism to share it. Do you know what I mean? Like maybe they collected on a certain population with an accelerometer that they built or that they, or algorithms that they developed. It's very difficult to get that data to the rest of the group. Whereas what we focused on was, I don't care what kind of hardware you use, just let us know. And you know, Alan is kind of our database guy, and the answer, Alan's answer to most everything is, yeah, I can do that. So somebody would say, hey, I want to look at the Aura ring. Can we get that data into the database? And Alan says, yeah, I can do that. And he figures it out. So now all of a sudden there's a whole bunch of Aura ring data, and I let everyone know that we have these data available now. And then that naturally attracts, it's like moths to a flame, where people say, oh, I really want to understand this. Can I use that data now? So that's been a really nice collaborative point. And I think if we had divided our attention between hardware and software, we wouldn't have been able to do that.
Yeah, that's really interesting. It's kind of it kind of flips the script, as you said, a little bit, and brings people to the data rather than generating that data to get people to the hardware side of it. But okay, well, I think in respect of time here, again, I'd like to thank you, Reid, for everything and for being here today and giving a great talk. I'm sure if people have questions or other questions, they can reach out to you, or feel free to reach out to
Absolutely.
me. I can connect, and we can you know, keep these conversations going. I think it's really important, and the database side of it, the open database, is something that Ron and I deal with a lot. So it's great to hear there's always that push forward, right? So thank you very much.
Yeah, no, absolutely, my pleasure. Thanks for attending, and thanks for the great questions and the opportunity to talk with your group.
Thank you.
Great, thanks so much.
Have a nice day.